immense pleasure to introduce Tadmor, Eitan friend and also, frequent visitor of the department. Some years ago, we had the chance to have him giving lessons on topic which is in rapid dynamical evolution. And this is going to be connected to his talk of today, Emergence Behavior in Swarming Dynamics. Eitan is here for 1 month, so can have opportunity to speak with him today and on further day. And the floor is yours, Eitan, please.
Thank you so much, Albert. It's really a pleasure to be here. Thank you for offline and even those that are online. And without further ado, let me start. I will talk about, I will give an overview of the topic of emergent behavior in swarming dynamics. To begin with, just give you just 2 examples for swarming and flocking, which I give here credit to the group, the Italian group. Does it show?
Yeah.
It does. Good. Okay. So basically, this is the topic. And as Albert mentioned, 6 years ago, I gave here the lectures, Jacques-Louis, and I thought in 6 years, it's a good period now to look back and to see this was really ages ago. And what happened in 6 years? I cannot make in 1 hour an overview of everything. It's impossible. But I think I would like just to intrigue those of you who know, or those of you who don't, what is really going on from a subjective point of view. So without further ado, let me tell you what the topic is about. So it's about examples of emergence. I always start with this slide. And here, it's not just about flocking. Here's an example where you have collected the emergence of tissues from cells on a different scales, let's say, than flocking or school of fish. You also have dynamics, let's say, opinion dynamics or traffic flow or certain things that propagate on the internet, or you have non-living agents that come together. And I will mention all of these examples. So these are examples from different scientific disciplines. And what is the main topic that we are interested in? So here are the fundamentals that cover everything. The first thing is that we have a crowd of N agents which are driven by N pairwise interactions. And the interactions, they have different names. They call sometimes alignment or synchronization, attraction. The important thing, there are no collisions. It's not about particles. In fact, what is important here is that the agents, they are called active matters because they either have senses or sensors with which they probe the environment. That's the big difference from particles. So this is, in some sense, the active matter. This dictates the dynamics because we have here communication with the environment. And typically, the communication is local. There are short-range interactions. So we have to talk about the notion of neighborhood. And then the dynamics produces coherent structures that emerge over time and for large crowds. And they call these structures flocks or consensus or colonies. So here is an example. Yes, you see that. Yes. I will not concentrate so much on the beauty of the flock and how they form the geometry, but the fact that there is a flock, and there is a finite diameter of this large scale form. And so the point is that we move from local interactions to global effect. And the key question is how these short-range interactions translate into the emergence of higher order structures. That's the main question. Okay. So the talk, I will focus on one paradigm, which I call alignment, where we have N agents. Each agent is identified with positions or traits or properties. It's a vector, and it's driven by this system of equations. So let me tell you what the basic features are. So we have the agents, we have these properties or traits, we have a scaling parameter tau, which runs throughout the talk, and we have the pointwise interactions. So this is where the dynamics enters. This is the communication between a position and position J. And the only thing we have to remember is that this interaction is symmetric, and this form is antisymmetric. That's obvious, but it will come later on. So the agents interact with certain neighborhoods because this can vanish, so we have to take into account certain neighborhoods. And sometimes we do not divide by n as we used to. We know that when we scale by 1 over n, even in particle dynamics, it has nothing to do with reality. It's just about scaling. This is a scaling parameter, so it's important sometimes to make adaptive scaling. And the dynamics here is steering towards environmental averaging. So when I present this, I gave recently the Gibbs lecture. I would like to give you some canonical examples to convince you that this is a rich class. I mean, really, to a certain degree, unexpected how rich this class is. So I brought you 5 canonical examples. I will not cover all the 5 canonical examples, but I think they are important to realize how rich this class is. So here's the first class. The first class is the examples of pedestrians and sensor-based motions and so on. And the idea is that the state space is space of positions, physical positions, and for example, robotic agents. So they change the positions by taking weighted average of the positions, the gradients in space. So this is a discrete gradient in space. And now the question is, what are the phi? So we can take a function which is a function of a radial function of the distance. So this is a metric kernel, which is very reasonable if you want to do with metric, let's say, in the interaction between robots and other UAVs. On the other hand, it makes sense to take a function which is function of the crowdedness. In pedestrian dynamics, when you think about the realistic version of a dynamics, it's not a function between me and the other guy far away. It's the question of how many other agents are between me and the other guy in certain control volume. So this is a function of the crowdedness, and we refer to that as a topological distance. And the question that we can ask, for example, is when is it true that all the agents come together? In general, the answer is no. So here's a simple example. If you, two-dimensional example, you can see that you start here with this characteristic function and you end up with a certain concentration. But on the other hand, if you take the communication kernel to be 1 over r, if you take the 1 over r, it essentially means that you are dictate the dynamics by the orientation, precisely by the orientation, then you are guaranteed to come at a finite time to the same place. So this is the type of question that can be asked in this case. So this is example number 1.
So xi is a vector?
Yes, in 3D.
Phi should be a vector?
No, scalar. It's a radial function of the metric distance.
The linear equation on the left side, it's a vector. On the right.
Yes, yes. So I'm sorry, this is a vector. This is the difference of the vectors, and they are multiplied by a scalar weight.
It's not a function of.
It's not. I'm sorry. Yes, I don't know how to make it. Yes, phi ij is phi of xi minus xj. These are scalar communication factor. Thank you for asking. It's a point for me to clarify. And they multiply the difference of the vectors. Thank you. Thank you. Thank you, actually. Okay. And since I'm trying to give a broad overview, I almost do not give any credits, references. I wrote them down here if someone is interested. But okay. So this is the first example. Let me go to the second example for this kind of alignment dynamics, which is less obvious, and it has to do with ratings and opinions. So now the state space is a space of scalars, and this is the ELO rating model. So Arpad Elo was a physicist who was a very good chess player. He was very much interested in chess. And the idea is that now every agent is characterized by its rating, which is dynamically changing, and its strength or qualification. So to simplify the Elo rating model, the idea is to use the zero-sum game with the following. We have games, and they have random outcome, either +1 or -1, right? And we change the rating, so this is the Elo model, by taking the interactions between 2 players. So we take the interactions, we put the weight, and then we see one is losing, one is gaining. This is the difference between in the rating. And then we have to take into account the outcome. Now, I really simplify here the model greatly in order to fit it and just go and go here. I put here a parenthesis to mean actually that this is an any odd function. Okay. And also when you play a game, you cannot play simultaneously against everyone, it's sequentially. But essentially, this is the message that you get here an alignment model. And in fact, this is the model that is used by the Chess Federation and by the Soccer Federation. And I quoted here what is the interaction function, this phi ij, they're actually used by the Chess Federation and by FIFA, and tau is an important factor. And the idea is that the expected value of the outcome, of course, is expected to be the difference in the intrinsic strengths of the players. And in this case, in this model, it is true that over time, the expected value of the rating should approach the intrinsic strengths. And this is the works of Japan and Joka. And there's issue also about learning. And then from a different perspective, I mentioned here dynamics of opinions. So if the QI are just scalar opinions, there is a famous bounded confidence model when you take a different kind of interaction. So the question is, what is the interaction between changing opinions, changing ratings? And you can see that it comes from different contexts. The third example is something to do completely different with floating and swarming. So this goes back to Cooper and Smay, where now the state space is space of velocities. And you change the velocity by taking the weighted average of the difference of velocities. And again, these are scalar. These are the difference of velocities. And the scalars are not a function of the difference of the velocities, but the positions. And the positions is here. So actually, this is the second order model, because now it involves the positions and the velocities. And of course, the question is, what is the phi? And originally, it was something that was decaying with the function of the distance, or it could be something with a cutoff if you have a finite limited visibility. And okay, the fourth example, it's another example of swarming, but it's very important. It plays a major role more in the physics community and less so in the mathematical community. A huge impact, and it's used by many. So I will mention it throughout the talk, even though I will not analyze it. It's the space of orientation. So the idea is that swarming is quantified by orientations and not by the full velocities. And here's the model. So again, I adapted it to this concept. You take a weighted average of the difference of the orientations. Actually, this plays more over here. And then you add noise. And this essentially means to take the orthogonal components so that basically you stay on the unit sphere. And the important thing is that the interaction now is the characteristic function of a ball. So it's not something which has a sort of slow decay. And the positions is a fixed velocity times the orientation. And so there is issue here that there is a fixed speed, and the velocity is the fixed speed times the orientation, which keeps changing. There is noise, which I do not discuss here at all, but the tension between the noise and the dynamics is very important for the phenomenon of phase position. I cannot cover it here, and there is a whole literature, really a large set of the physics that are using it in birds, in locusts, in fish, experiments, and so forth. I have to mention the Vickshep model. It's a very important model. And the last example is synchronization, which comes from a completely different aspect. So this is the famous Kuramoto's model. And here the state space is a space of phases. So you have phases in S1, and you change the phases in terms of this formula. So the important thing here is that these are random numbers that we put one. This is one aspect. The other aspect is this kind of change of phases. You can see that if I take phi I to be the ratio between the sine and the thetas, then I get essentially an alignment with phi ij, which need not be positive. And you get a perturbation or initial phases omega I, which you assume that they have zero, and there is a tension between phases. And also here, there's a very large literature of phase coherence. There's a question about how big the initial phase, the initial perturbation of phases versus the alignment. There is no point for me to try to cover everything except to show you one example which I took from the internet, and you can see that if the alignment is very strong, okay, essentially, if the alignment is very strong, you see that there is a complete coherence, there is a full phase locking in coherent motor oscillators, and if it's not very strong, then you can still see the effect of the initial. Yeah. Okay, so these are 5 examples which are completely not related, from completely different corners that I brought under the alignment model. And the important aspect here is this communication. So everything is dictated by what is the communication kernel, or what is the rule of engagement. That basically is the main story. And different communication kernels appear in different scientific disciplines. So the question is, where these kernels come from? Everything is that I know, where do they come from? It's not dictated in a uniform way. So let me mention that few examples. This is a busy slide. I just show you that in flocking, for example, these are phenomenological. I mean, it's not coming from anything except for the fact that you have a general phenomenological rule, which is, well, the interaction depends on the distance and it decays with the distance. It's a phenomenological origin. Another comes from observation. So what I told you about topological kernels, namely it depends on the crowdedness, it's actually from experiments. So there is the Starling's, it's not just experiments, but it's a long process of the group in Rome. This is one example, and I can give you another example about human crowds. In both cases, there were experiments that show that the interaction does not depend on the distance, but it depends on the crowdedness, the number of agents which are between me and my neighbor. So this is another source of what kind of communication kernels we have. Another source is random-based protocols. So I already mentioned just briefly about the ELO rating, because clearly when I play a game, I do not interact with everybody. It's a random process with whom do I interact. That's very important. And it also appears in phototaxis, this kind of random interaction. Another source for the communication kernel is learned from the data. So in this age of machine learning and everything else, I just make here a few references where you look at the data, and then from the actual data, you try to make the inverse study of what is the phi. And then finally, there are some higher order principle how you derive the phi. For example, there is a minimum entropy principle, and there is another higher order principle I refer to as an anticipation, and it is this one which I would like to continue. Just as an example, where do I get this communication kernel which is so important? So, anticipation. So here's a simple way to derive alignment model. So I'm now going higher. I start with a simple familiar dynamics. Looks like the Hamiltonian dynamics is not. The only difference is I start with a potential. So there are positions and there are velocities, but the only difference is that the potential is evaluated the distance, not of the positions, but the anticipated position, where tau is a small positive parameter. So actually I react not to the state, but what I anticipate will be the state, which we will agree is something which is realistic in different contexts. So what will be the effect of taking standard Hamiltonian system and particle system and adding this anticipation? So the answer is, let's expand it in a small parameter tau. So the first term is given here. It represents reaction, repulsion, and attraction, which is familiar to us. But the second term is interesting. When you take the second term there, you get a matrix. Now it's a matrix, not a scalar. This matrix has to do with the Hessian of the potential, and this matrix multiplies the difference of the velocities. So in a very systematic way, what we get here is essentially repulsion, attraction, and anticipation implies alignment with matrix coefficients. And of course, if tau is 0, then we go back to classical n-body probe. So in some sense, in my mind, I mean, you give me the potential U, and then I get a matrix of phi, which is the Hessian. And if I further reduce the matrix to scalar, then I go back and I derive in this fashion. And what is called the three-zone model. The three-zone model essentially means that we have repulsion and alignment in three concentrating regions. First, we have repulsion, then the outside we have the cohesion or attraction, and then in between there is an alignment. And the person who is responsible for this three-zone model, one of those, but I mean, he plays a critical role. So in 1987, it's Craig Reynolds, and he came with this three-zone model for repulsion, alignment, and attraction. And instead of so many words, let me show you the key role of alignment, because that's what I'm talking here. So here is a simulation that is taken again from the internet, but it's beautiful simulation. And what it shows you, he called it voids, Craig Reynolds, birds-like objects. And you can see that they do not impinge, there are no collisions. They stick together and they somehow, they're like birds and they steer in the same directions. So this is basically the dynamics of this three-zone model. And it's rather realistic in this aspect. Now alignment is turned off and it becomes, it's not realistic anymore. It's still without collision because there is attraction and repulsion, but there is no alignment. So alignment is the main feature that really makes this thing kick in what we want to have there. And indeed, you will see, once turned off, it comes back to something that we try to understand. So let's wait a second. Yeah, it's true. Okay, well, I have to align my time too. So once you click on the alignment, you can see immediately that so now you understand why I focus on the alignment dynamics, in addition to attraction and repulsion. By the way, talking about Craig Reynolds, he received the Oscar for that, for technical achievement. And till today, there is no complete analysis of the three-zone model. In fact, I'll explain what is the difficulty about the local aspect of the three-zone model. I mean, we are still missing a big piece there. One question I would like to ask: fluctuation. What is one? One is nothing but summation, integration by parts. I take into account that the phi ij is symmetric, and the interaction here is non-symmetric, anti-symmetric, and dissymmetric. What about the second inequality? Well, the second inequality, this factor lambda, is in fact the second eigenvalue of the graph Laplacian, and this estimate is sharp. So we conclude that because this estimate is sharp, if we want to take everything, we conclude that if we want the energy fluctuation to go to zero, if we want everything to align in the same direction, the fluctuation should go to zero, this will happen if and only if the integral of the second eigenvalue of the graph Laplacian tends to infinity. And this means that the graph is connected, just in the usual sense of connectivity. So every vertex, every agent should be able to communicate with every other agent, maybe not directly, but through intermediaries. And not only that they are connected, but they are connected in a quantitative way so that the tail tends to infinity. Then and only then, you will get that the fluctuation tends to zero. So it's the first time that we see that there is issue of connectivity. So now I switch to the language where there is phi, which is a communication kernel, and the communication kernel is responsible about connectivity of everything on the graph. Okay, so what happens when we have long-range communication? Well, it turns out that we can find out the lower bound for this so-called Fiedler number, which is given by the behavior of the kernel along the diagonal. And as a consequence, if we're talking about metric kernel, and if this kernel below is slow enough with beta less equal than 1, so it has a heavy tail, which is non-integrable. So this means in this case that everybody talks to everybody else directly and with a heavy tail. In this case, we get unconditional flocking. And in fact, the statement is true if you have alignment and if you have attraction. Even if you enter attraction to that, it still works. So there's a lot of that has to be done behind the scenes there, but I don't elaborate that. So essentially, the statement is if you have long-range communication, then everything comes together and then they will align in the same direction. But there is one thing that we do not know, namely, what happens if there is a repulsion? What happens if you get too close, then things sort of push away everybody else? because now there is a balance which is very delicate, and this is exactly where we miss something about the three-zone dynamics, but this is really the important thing. So we really know not as much as our, there is no result about alignment, attraction, and repulsion. Okay, so we know now something about the long range. What is the long range? We need that the integral, the tail of this communication, infinite tail, it should be non-integrable. So we have to be able to communicate with those that which are far away in a meaningful way. In this case, you will get consensus and flocking. But what happens if we have short range? Suppose, which is more realistic, what happens if we just interact with those that are close to us? So here's a counter example, which shows you something I showed it many times, so for those who see that. So that before, so the idea here is that you get a distribution of opinions. These are scalar opinions, numbers, just numbers between 0 and 10. This is the interaction, which is a characteristic function of the interval 0, 1. You can see that every person is connected to every other person, because this guy connects to this guy to this guy. Eventually, all of them connected through intermediaries. So they definitely talk to each other. But when you run it over time, you see that the opinions concentrate into 4 different parties, and they do not communicate. So something breaks down. And what breaks down is precisely the Fiedler number of the graph Laplacian. The geometry of the graph Laplacian changes. So you see, this depends on this file. On the other hand, if I change the communication with something which is less intuitive, where I pay more attention for those who are further away, and those which are close to me, I pay less attention, namely it does not decrease, on the contrary, it increases, then there is a consensus. So you can see that there is some sort of delicate issue here about the discrete behavior. And it has to do with the fact that this discrete behavior with short-range interaction is unstable. And in order to overcome this instability, I moved to discuss the hydrodynamic description, the large crowd description. So the idea is that when you take large crowds, not a fixed N agent, but when you take large crowds, then this kind of instability or unexpected behavior will be washed out under the large crowd behavior. Of course, it will bring new questions. So that's exactly bringing me now to the second part of this talk, the large crowd dynamics. And the large crowd dynamics is captured by the empirical distribution given here. So again, this talk is given in different crowds, so I have still to justify about the passage from the discrete to the continuum. And it's captured, the large crowd dynamics is captured by the moments of these empirical distributions. So these are the moments with respect to the velocity. And we assume that all these limits exist. And if these limits exist, then we call these limits the density and the momentum. And before I continue, so just in order to make sure, it's another simulation of Sebastian Mott, which I like, which actually clarify better than everything. This is actually the Vic-Check model on a 2-dimensional torus. And what you see here, and now you understand why the fascination about the Vic-Check model, because it's really interesting, right? You do not get you get 4 larger forms being created here. And so here it is the discrete form, and what you see there is the description corresponding to the discrete form in terms of the density and the momentum. And you can see that you see just the direction and the intensity, and you do not need the detailed information. So I would like to move from here to here. So a lot of work was done on the passage from the discrete to the continuum. I mean, I cannot mention, there are really many, many works. So I just mentioned a gap from, down there. So my friends will excuse me for not mentioning everything. And here's the hydrodynamic description in terms of the density and the momentum. So these are the familiar equations for the mass and the momentum. Here's the pressure, and here is the alignment. That's the only difference. That's the only term that remembers that we have a new aspect of the dynamics, alignment. What is the alignment? It's given here. There is a kernel. And then we take the gradient at every point. Here's the point x. And we integrate over all x primes with the density rho prime over, let's say, we take the whole space. Okay, so here's the alignment term. Now, what about the pressure? When you come to the existing literature, usually, well, the pressure itself formally is derived by the second moment. And the second moment, of course, there's a problem of closure. So I leave it as it is. In fact, I do not know what the closure of the pressure is, because there is no natural Maxwellian in this case, because the phi could be anything. So just let's leave it as some tensor, and this is it. So in fact, this is not a hydrodynamic description, because this is some tensor that is derived from something that I did not tell you what is the limit, and I leave it as, I would say, as a incomplete hydrodynamic description. And in fact, at this point, let me quote from Sheck and Zafari. Said this is a very important paper. And they say that the source of energy, if you want to close it, you have to deal with the energy. The source of energy making motion possible is not relevant. What they say in their model is that when you think about collecting, that these are not particles. You cannot talk about the conservation of the energy, because the energy is something that comes from the outside. So it makes no sense to say, oh, there is conservation of energy. And that's a very deep statement, which I partly agree. I agree that we cannot make the bookkeeping of the energy for the non-particle examples that we are discussing here. However, I would claim that even though we don't have thermal equilibrium, I would replace the equalities by the inequalities. And this is what I'm doing right now. So I take a pressure and I define a mesoscopic pressure. Mesoscopic pressure is something that comes from somewhere, but I don't attach it. And this mesoscopic pressure is something that its trace is non-negative, and it satisfies this inequality. This inequality is somewhat formal. It's reminding the notion of dissipative solution for in the compressible equation of Lyon's. I mean, there are many contexts where this notion of a dissipative, I call it mesoscopic pressure arises. And the point is that any closure which comes from a kinetic description fits this inequality. In fact, it satisfies equality. Any closure. In particular, when it's monokinetic, when there is no pressure, it of course satisfies that. So I take into account all the inequalities, and I do not make precise bookkeeping where the energy disappears with. It just decays. The remarkable thing is that even though I leave it unclosed in some sense, the alignment is a very strong term. So here's the point. Let's look again at the energy fluctuations, just as we did in the discrete case. Now these are fluctuations, macroscopic fluctuations, and this E is the internal, essentially the quantified internal fluctuation. And the statement is that if we want to see how this fluctuation behave, first of all, they decay in this fashion, and this follows exactly from the definition of the pressure. So the pressure essentially is responsible for the statement, energy cannot be gained in any system, living matters or not. It cannot be gained because it has to come from the outside. It can be just lost. So this is statement number one. And statement number two, I still want to bound this, and the bound is that indeed it's bounded by this second eigenvalue. Now I move to the torus, because I need discrete spectrum, the second eigenvalue of some weighted Laplacian. If you want to know what the weighted Laplacian here it is. You're not interested. You're really not interested in this operator, which is weighted Laplacian. And the only point is that now I can bound this entropy by the second eigenvalue, and therefore I get exactly as before that the fluctuation decay if the second eigenvalue is large enough, which has heavy tail, just exactly as before. And this is true even if we have pressure. So now let's revisit what we know about long-term interactions. And just as before, we will see that if we have a kernel with a long-term tail like this, then indeed what happens here is that we have this lower bound on the Friedel number, or the second eigenvalue. And therefore, now we need another thing. We need something about the crowd that we are talking about, namely the support, the diameter of the support. If the diameter of the support does not spread too much, then what is too much? Well, if it goes like some power of gamma, and we have the decay of beta, if beta times gamma less than 1, then basically we get flocking. That's basically the main statement. So I don't prove these things. It's not the right framework. But this is an important statement because it tells us for the first time that we have a support, and we have to see that the crowd does not disperse too fast. If it disperses too fast, there is no crowd, there's nothing to talk about. So if it does not disperse too fast, then within the crowd, there is an alignment, and then there is a cohesion to go, and there is a preferred direction to move. So something emerges, exactly as we see. So there is now a question of how fast there is the decay of the communication, and how fast there is possible growth of the diameter of the crowd. Mm. And if gamma is less than 1 over beta, then in fact all the fluctuation and the pressure go to 0, everything. Okay. So now the question, what do we know? Well, what I know in the literature is that if you have a monokinetic closure and beta is less than 1, then gamma equal to 0. Everything decays exponentially. Notice that this requires a monokinetic closure. If you have matrix interactions, then for beta less than 2/3, then there is the right mapping between beta and gamma. And then finally, even if you have pressure in 1D, which is quite remarkable, even if you have pressure in 1D, again, more than 1D, and if you now put a kernel which is singular at its head, so you put a lot of emphasis about the immediate interactions, and then the tail is the usual long tail, then it follows that there is unconditional flocking. And again, this conditional flocking independent of what the P is. And the reason what is responsible for this statement, because otherwise it's not true, because I do not control the velocity, I do not know anything about the velocity. The reason that it's true is that alignment is a very strong, in some sense it's stronger than a elliptic operator. It is elliptic but fractional. Okay, let me skip maybe, there are also the issue of external forcing, right? I always talk about alignment, here's external forcing. The reason I brought it here is just again because of there's a beautiful move that. So we show that actually not only the things align, but they also concentrate a lot in moving harmonic oscillator, and that's okay. So now we come to the question about short-range interactions. In some sense, this is what I'm targeting. So what do I know about short-range interactions? So let me give you three examples. The example number one is when we have metric kernel. Now I have to be very specific when there is metric kernel. So I know that the rate of change of the energy fluctuation is given here. And now this is a torus. So how negative is this, and the decay rate of the energy fluctuation, of the entropy? So how negative? So one aspect, of course, is if you take the mean of the interaction outside, this gives you what I've done before. So basically means if the interaction is long range. But now I want short range. So here's the statement. If you take this kernel phi, which is on a torus, you look at its Fourier, its integral is a constant, A. If you look at all the Fourier coefficients which are different from 0, you want them to be uniformly bounded away from A. If they are uniformly bounded away from A, so it's something about the discrete Fourier coefficients of the kernel phi. So I call this coefficient sigma, and then it turns out that the Friedel number, or the second eigenvalue, has a lower bound, that's what I'm looking for, in terms of the sigma and in terms of the mean and the max of the density. And so let me now slow down, because maybe this is not a sharp result, but it's an important result. Because it tells us two things. First of all, there is a property of what is the communication, with a short range communication. So phi could be a short range, as long as this quantity remains strictly bounded away from 0, sigma phi is positive. But this is not enough. We still have to control the mean of the density and the max. So the max cannot be too large, and the mean cannot be too small, in the sense that we cannot get too close to vacuum. And now slowly we start to, okay, so now there are some examples here, which are fine. It's interesting just to compute them. But, and of course, this statement is true independent of the support of phi, independent of the thermal, the internal energy and the pressure. So this is pretty pleasing, except it requires one thing. It requires to control the density. So whenever I look at the hydrodynamic equation, I always pay attention to the velocity, and the density is sort of being transported. Here, the issue is not that the density is being transported. Here's the issue, that you start with a group or crowd, and you can approach a vacuum, and then you create holes. Now, if you create holes, or if you break it, then you destroy your communication. So it is really essential to control the minimum of density. It's absolutely essential. So at the beginning, it sounds like, well, let's control the minimum density, but it turns out to be a very difficult problem because you have to quantify how close it is zero over time. What is the behavior? And it is the density that holds the information for the propagation of information. So once again, even though I went to the hydrodynamic description, you see that there is some sense of information and the propagation of information. Whenever the density is positive, information propagates. If there is zero density, then the information does not. Here's a second example for short-range interaction. This is in terms of topological kernels. So you remember, in the topological kernel, we measure the distance not in terms of the metric distance, but in terms of the crowdedness, which is essentially the mass between x and x prime in some controlled volume. Here's x and x prime, and here's a typical controlled volume. You cannot take, so this is a controlled volume with tips at x and x prime. So you define the topological distance, and then you look at the short-range protocol. So this is short-range. I just look at my neighbors close to me, and then the interaction is proportional inversely to the crowdedness. Okay, this is very realistic interaction. The only trouble is, and it has to be inversely realistic to the crowdedness. So this means that as the point x and x prime approaches each other, this becomes singular, and therefore one has to. Okay, so first of all, why topological? Because this is essentially the same thing as what I said before, that you count how many agents are close. Now, working with this on the continuum is not trivial because this is a singular integral, and so basically we're looking at this kind of dynamics. So this is the usual transport. There is no pressure. But this is the alignment. So you get u prime minus u, and then you take the interaction, which is in the small neighborhood, and then this is a singular term. So you have to make sense. First of all, you have to make sense of this singular integral, which is not trivial because not only that it's singular integral, but it lacks symmetry because of the density. All of this was done in this work with Roman Schweikart. And eventually, when at the end of the day, in 1D, we proved that smooth non-vacuous solution flow. So first of all, you need smooth existence of solution. And then if the density is bounded from below by 1 over 1 plus t, so if the density does not go to 0 too fast, then there exists global smooth solution and it will flow. So this is the true, only one example I know for short-range interactions that flow. And then let me conclude with a third example, which I already announced in the abstract, which I found amusing, again, about propagation of information. So this is about multi-species. So here's what the equations we are talking all the time, but it's a little bit noisier. So let me tell you what's going on here. First of all, there is no pressure. Let's put pressure aside. And secondly, if there is no index alpha and beta, then it's exactly what we had before. There is alignment, and there is transport, and this is it. But now, in realistic cases, the interaction, there are different species. So what does it mean that we have a different species? It means one species, let's say species alpha, is distinct from the other species because they have different rules of engagement. So if all of them, they have the same rule of engagement, this is it. But if they have different rules of engagement, then each species is identified by the rule of engagement, how species alpha interacts with species beta. So it's some scalar functions, some scalar rules, let's say metric, that they interact among themselves. Okay? So you should think that there are, say, 5 groups. How many, doesn't matter how many groups, and different groups interact with different rules with the other groups. And the interaction is alignment. So this is basically alignment dynamics for multi-species. And just as before, we have to look at the energy fluctuation, which I don't even write here. It's the L2 of all the changes. And I want to show that everything goes in the same direction. When does this happen? So it turns out that the rate of change of the energy fluctuation is given here. So you see, you have to take into account the fluctuation between all the species, alpha and beta, at all positions weighted by beta, and this is the diameter that I still have to control. Essentially, that's what you get into. And now you have to find the lower bound for this entropy, essentially. So how do I get the lower bound for this entropy? It's not exactly what we had before. Before it was the same U. Now these are different velocities from different species with different weights. So the question is, what do you do here? So here is a statement, correlate equality for set of vector value functions. So the idea is that these are the U alphas, these are the U betas, these are the densities, and this is some matrix here, I call it A alpha beta. And I have to find the lower bound for this kind of entropy. And the statement is that there is a lower bound, which involves the second eigenvalue of some weighted Laplacian, not the Laplacian associated with A. With every matrix A, there is a Laplacian. Weighted Laplacian, it's a Laplacian depending on the ends, the weights. These are the integral of the rows, and they are usually conserved in time. So again, I do not be discussing the details. The important thing here is again that there is spectral gap here, and this is outside again the fluctuations. So this statement is true. So we have this inequality. But when you look at this inequality, there is something strange. In fact, it seems that it's wrong. And the reason is, the question is, what about the self-interaction? You see that this sum takes into account all the terms which are different from beta. I just take into account all the species different than mine. What happens with interaction with my species? I don't care. And then on the right-hand side, I get all the alpha and betas. So for example, if you take the term, which is the sum of alphas, U alpha x minus U alpha x prime, so just the interaction with my own kind, it is not here, but it is there. So how could it be that the term that is not there appears there and still I get the inequality, right? And the answer is, it is true, and it's again shows you the power of communication. The lambda A is in fact, this figure number is independent of self-interaction. So indeed, this number is independent of self-interaction. And in fact, it allows many A's to be zeros as long as the array, the matrix A is connected, graph connected. So what happens, suppose I want to interact with my own kind. I don't know anything about my own kind because it doesn't appear there. However, I interact with another group, and this other group interacts with the third group, and the third group interacts with my own group. And through this, the information propagates. And because of that, this inequality is true. So again, you see that information is always there, even if it is short-range interaction. And once you have this lower bound, that's exactly what we are looking for. And therefore, we have a statement that if the second eigenvalue of the weighted graph Laplacian of this matrix phi. So now this is scalar numbers, but I look at them as communication array because they tell me what is the communication rule between the different species. And if the communication rule says it is connected, even though it could be a short range because many times there are zero, then the information propagates and everybody will go to the same average. So you can think of it as like a game. Here's an example. Suppose you take a matrix phi, which is 0, 0, 1, and 1. So this essentially means that I look what happens to my neighbors and my neighbor looks at me, but I never interact with my own kind. Then everybody will go to the same global average, even though that there is no self-interaction, just because of communication. Okay, with the 2 minutes that remain, so these are the 2 examples I want to say. I want to say two things. First, since this was about 6 years from the past, a little bit for the future, open issues in Smallman dynamics. So I want to tell you what I did not tell you, because I know very little. One thing which is extremely important is about boundary conditions. I didn't say a word about boundary conditions because I really know very little. This issue, for example, comes in Perry dynamics, where in Perry dynamics you have something similar to what I discussed here about alignment. And the solution that, for example, you should do in this group, they take a communication kernel which is sort of adjusted to the distance from the boundary, but they never treat the boundary. So what are the boundary conditions if it's not Neumann for this kind of alignment? What should be really the boundary condition when you get a flock of birds? And what should be the treat? What is really going on there? It's not clear. I mean, I don't know. The second thing I told you already, repulsion. I know very little in the literature, not just for me, of works that deal with the case that there is alignment and repulsion. Now, the balance between repulsion and boundary condition, this will dictate also the geometry of the support. So I just gave you the statement, what happens that everything emerges towards the average, but it's more interesting. I'm not able to capture because there is not a complete solution. Then there is a role of a pressure, which is not clear. The pressure seems to go to the monokinetic phase as t tends to infinity. It's not clear. And finally, there's the issue of modeling. I mean, I concentrated on one model, which is inspired by Cook and Smale, but for example, Vichek model. So maybe the last slide I will conclude with things which come from the broader context. So here is something which is completely subjective, has nothing to do with anything, but I just feel that it's important that I will tell you a few things. It's not just what I'm doing or what I know from other scientific disciplines. So for example, in biology, collective dynamics, there is a very important issue about empirical data, believe it or not, right? I mean, it's important to be attached to the reality. You see, the dynamics of ants with smell, and the dynamics of bats with sound, and the dynamic, let's say, of locusts with the gravity, I mean, these are completely different. You have to take them into account. And there is a large literature. I just know the works of Nir Gov about ants, and phenomenal talk that I heard like 3 years ago, and the works of Ian Cousin. I just completely subjective, biased choice of 3 names that I put here on the slides, but it's important. It's not just the mathematics of everything. In physics, there's a question of order and disorder and complex system and criticality. So I already mentioned this review of Vichek and Zerveris, and then Bialik, and then just recently, there is this review article on active matter. Believe it or not, but this review article, I mean, the word Cook and Smale is not mentioned there once. It's just completely different world in physics community about criticality. Now, in computer science, well, actually, Slepchev gave the other talks here of, now that I got to think about it, the Lyon's talk about clustering dynamics on graphs. And then in engineering, this issue of synchronization and delay, I don't even bring here references. And then in social science. And then finally, I would like to conclude with computational methods, non-convex optimization. So here's one reference to the series of work of Carrillo and others. And now we are working on this as well about consensus-based optimization. So think any numerical algorithms where you have one agent trying to optimize something. Now you have many agents trying to optimize the same thing. Fine, just multiply. Now think of many agents that communicate and they try to share the information in order to improve the situation. So this is exactly the consensus-based optimization, and we have consensus-based gradient descent methods, and so on and so forth. And I thank you for your attention.
Thank you very much. Concrete questions, maybe, I don't know, from the remote audience, are they?
To observe this what is happening. Is it possible to get the file?
You mentioned that.
Yes, that's what they do. But the point is that if you want to understand this, right? So there are 2 things I see here. First of all, they stay together. The diameter is fixed, right? This is the one thing I try to concentrate. If you want to find the geometry of the support of the boundary, right? You have to take into account reaction and repulsion, external forcing. You have to take this into account. And perhaps in the boundary conditions. Perhaps the most important thing are the boundary conditions. So that's the reason I leave it for the next 6 years. Not me. Yeah. I know it's fascinating when you see it. You say, okay, let's try to replicate this to understand it. I'm not at this stage. I mean, at least my understanding is limited. I just really, this is the reason I titled this "The Mathematics of Swarming Dynamics." There's still a gap between trying to, but this is not the only model. You see, flocking. I mean, cells.
Olivier?
Suppose your food comes in, nutrition, in terms of fish. Is that an external force on the ingredients?
So I want to say 2 things. First of all, about food. So clearly, this is an impact as far as the energy is concerned, because this is coming from the outside, right? So this is exactly the interpretation of what Vichek said. When you talk about this kind of agents, you cannot do the bookkeeping of the energy, because it's something that is a different scale. It comes as food, it comes from whatever it is. So this is number 1. Second aspect that I want to address, you asked me whether or not food is important for dynamics. I do not know, but I can tell you that now you come from the mathematics and the physics to the biology. So in fish, for instance, which is really important, is the temperature of the water. 1 degree in the temperature of the water completely changes the dynamics. Not that I know this, but I just learned it because of my ignorance. I thought, well, it's mathematics. But it turns out that the temperature of the water is really important. So now we're talking about external environments, that situation. And you cannot just create it from some basic principles. You really have to understand it from the context of biology, from the biological aspect.
Luis?
So, yeah, you mentioned Kaniadakis as one of the references.
Yes.
So my naive question is the techniques
Yes, it's Kaniadakis
what is the impact of it?
Yes, Kaniadakis is one group, but there's another group of Kaniadakis, I cannot cope with Kaniadakis because this is he does everything, right? Yes. Okay, but he did, it was pretty impressive. But there is another group of Maggioni in Johns Hopkins, and he is doing a long-term project trying to learn all sort of interaction rules. It's impressive. I don't know what to say more than I'm just aware. In fact, my former student is one of those. He's doing the work. That's what I can say. Yeah. In what sense?
No, I mean, this is 6 years since the
yes. So
I guess for them 6 years.
Yeah. So let me tell you, that's a good question. This is a good question about, once you talk about this machine. Okay. So it goes like this. Let's take the groups that Maggioni and Kaniadakis, and they started to learn what is the phi as a function of the distance. Then came the experimental group, and I mentioned it, and I put it in red, of course. It's centered around Parisi because he got the Nobel Prize, but it's the Italian group, let's call it. And there, I don't know for how many years, they observed the starlings over Rome train station. And in a very systematic way, I did not read the whole set of papers, they concluded that the interaction is not metric, but it's topological. Every bird reacts to the 7 closest birds to it. The number 7, I remember. Can you learn this, or do you have to observe it? That's a fundamental question, because about the learning, nothing will help unless you have a priori knowledge and okay, it's not metric, it's topological. So maybe the observations are more important. Once you know enough of the observation, then you can you see, because all the learning, basically, the most important thing in learning is the training. But you have to train for certain knowledge. So you have to know something. You cannot get something out of nothing. And according to the second law, you cannot get even nothing for nothing. But it's you have to train something. So I think that the experiments are still, it depends on what topic or what area, because it is very broad. I think that still there is in the biological examples, the experiments takes I think, first row before even learning, observations.
Other questions? So if not, thank you very much, Eitan.